All right, so has everybody turned in their homework?
No. Come on, Danny. You already know he's going to grade that one. Yeah.
All right, any other homeworks? Cool. All right, so questions on the homework.
The last one. No, it was 8. It's number 8. He doesn't even remember which one.
So what was the question? I don't want to bring up Canvas.
It was use modular or exponential stuff.
Modular exponentiation. And what were we trying to do?
7 mod 8.
Use modular exponentiation
7 to the
calculate
power of 520 mod
13. 7 to the 520 mod 13.
All right, cool, we can do that. So let's find 7 to the 520 mod 13. So there's two ways to do these things usually: Fermat's little theorem and modular exponentiation. Okay. Modular exponentiation, we're going to calculate powers of our number where the powers are powers of 2. So in this case, we're going to calculate 7 to the 1, the 2, the 4, the 8, the 16, the 32, high enough that we can calculate 7 to the 520 by multiplying together 7 raised to other things. So as soon as the screen warms up, here we go. Okay, so start calculating powers of 7. So 7 to the first is easy, that's just 7. 7 squared is 49, and what's the remainder when you divide 49 by 13? Right, so it's 10 more than 39, so that's congruent to 10. 7 to the fourth is the square of that, so that's congruent to 10 squared, which is 100. And what's that when you divide it by 13? Close.
9.
Is it 9? Yes, it is. I didn't believe you. I thought it was going to be something different. All right. So one way to do that is 10 is also congruent to minus 3. And minus 3 squared is 9. All right. So 7 to the 8th is what? 81.
Which becomes 3.
I'm going to trust you this time.
Thank you. The next one's 9.
All right. So now we got a pattern. And we can stop there, which is good because we're out of paper. So we want to find 7 to the 5/20th. This is 7 to the 512 plus 8, which is 7 to the 512 times 7 to the 8th. And we know 7 to the 5/12 is congruent to 3, and 7 to the 8th is congruent to 3. So this is congruent to 3 times 3, which is 9. That's a good answer, mod 13. And usually when you're doing these, you'll find a place where you have some kind of pattern that's repeating. And then if you write carefully, you can just sort of fill it in without having to do too much actual calculations. And then it's just adding up the exponents, multiplying what they're equivalent to. All right, does that make sense? Yeah.
Just to clarify, when you're doing the multiplication of 7 to the 512 and 7 to the 8,
Mhm.
is that also mod 13, but since it's less than 13, it just becomes itself, which is 9?
So, yeah, so everything on this page is mod 13, right, except that 520 is 512 plus 8. But yeah, this is actually equal to 7 to the 512 plus 8, which is actually equal to that times that.
Yeah, so the mod 13 would still be there, you're just not showing it?
Yeah, yeah, mod 13 should be on all of these. All right, other questions? Was there a Fermat's Little Theorem question on there? Okay, thought so. You okay with that? Yeah. As long as you tell me what it was asking.
Use Fermat's Little Theorem to calculate 101 to the 221 mod 23.
All right. So it's helpful to write down what Fermat's Little Theorem is because you get some points for that even if you don't know how to use it. Which says a to the p minus 1 is congruent to 1 modulo p. As long as a is not a multiple of p. So we're working mod 23, so we've got to let p equal 23, which means anything raised to the 22 is congruent to 1 mod 23. Well, we're asking a question about 101 raised to something, so let's let a equal 101. And Fermat's Little Theorem tells us the following then: 101 to the 22 is congruent to 1 mod 23. So we know this for free, and we're trying to prove what this is equal to. We're trying to find what that's equal to. So how do we go from something to the 22nd to something to the 221st? Yeah, multiply it by 10. So a to the b raised to the c is a to the b times c. So 101 to the 22nd to the 10th is equal to 101 to the 22 times 10, which is 101 to the 220. And since 101 to the 22 is 1, 101 to the 22 to the 10th is going to be congruent to 1 to the 10th, which is still just 1. So we've just slashed our way through 220 multiplications with virtually no work, and we've shown that 101 to the 220th is congruent to 1. Well, how do we get to the 221st? Just multiply by 101. So 101 to the 221st is the same as 101 to the 220th times 101, which is congruent to 1 times 101, which is just 101 mod 23. And so what's 101 mod 23? So 9 more than 23 times 4, so it's 9. So there's your answer. All right, so Quiz Friday, you're going to have 5 questions. I'm asking you to do 4 of them. 2 of the questions will be, one will be modular exponentiation, one will be Fermat's Little Theorem. So if you know how to do these 2, you've got 2 of your 4 problems done. One of them is multiple choice, one of them is calculating modular equivalences, and I don't remember what the 5th one is. So if you know how to do this, right, and you can do a multiple choice about prime numbers and number theory and modular equivalences, you're done with the quiz. Okay? Yeah? Yeah. I don't remember how many, but it says on Canvas, I think. It's either 4 pages or 8 pages.
8 pages if you want to use the font.
8 pages, single-sided. Cool.
300
Thank you. 300,000 billion pages. Yeah. I'm planning on like a half hour, but if people finish early, we'll finish early. If nobody's even started after a half hour, we'll go later. It's hard to time out quizzes, but it's 4 questions, and like I say, 1 or 2 of them are just fill in the blank. So.
So is that other one extra credit?
Nope. Yeah, you can only do 4.
Oh.
I
Oh,
know.
so it's pick your own, I see.
Pick your own. If you do all 5, I'll take the first 4.
This is a full multi-choice.
Yeah. All right, other questions? Yeah.
So there was another one of the problems that I think we actually did it in class, but I was thinking if I'm going to do it, it was basically proving the A divides or something divides A minus B.
Yeah, if A and B have the same remainder,
Yeah, and basically the only thing I could think of was just the definitions that we've been given.
that's all you need. Yeah.
That was,
So suppose A and B have the same remainder when divided by n. I think I divided by m, so we'll do m. Prove that m divides their difference. So A and B have the same remainder when divided by m. That means A is congruent to B modulo m. And we made the statement in the beginning of this that if 2 numbers are congruent, that's the same thing as saying that m divides their difference. So I was asking you to show that in a proof. And really, the only thing you have is the definition. A over m has some remainder r, right? And b over m has the same remainder r. Right, that's your hypothesis. And when you divide each of those by m, you get the same stuff left over. Well, to say that a divided by m has a remainder r means a is equal to m times, some integer plus r. So I is an integer. And this second statement is saying that b is equal to m times some possibly different integer plus r. All right, so that's the definition of dividing and having a remainder. And now if I write a minus b using these expressions, that's mi plus r minus mj plus r. And the r's cancel, so this is just mi minus mj, which is m times I minus j. So that's all algebra. But now we've written a minus b is equal to m times some integer. And that means m divides a minus b. That's the definition of divisibility. So that's not a lot of fancy algebra, it's just sort of lining up the definitions and letting things happen. Other questions? Yeah. Mm-hmm. I would give you credit if I didn't actually say don't use modular arithmetic, because technically that's correct. I'm not grading that one, but as long as you weren't told, right? So I mean, that would be the power of modular arithmetic, is like if we know that a and b, so this is really just saying a is congruent to r and b is congruent to r, so a minus b is congruent to r minus r, which is just 0. And if something is congruent to 0 mod m, that means m divides that something. So yeah, that comes out pretty quickly like that. All right, other questions? All right, so I said I was going to do crypto systems today, but I changed my mind. I'm going to skip over crypto systems. We'll come back to it if we have time. But there's enough other stuff that we need to cover for this course that I want to move on, and then we'll come back to that if time permits at the end. That's an application of number theory and some of the stuff we've been doing. And it's interesting, but it's not something I ask about on the exam. And it's not something you're really going to necessarily build on unless you're doing cybersecurity, in which case you'll see it again. So I want to move on to another unit, which is about counting. And this is a subject that will be useful in your transfer destination when you deal with statistics and such like that. And we'll spend a few days talking about this. This will get us into combinations and permutations, okay, which is important stuff, and it's important computer science-wise. And then I want to talk about automata theory for a few classes, and that's definitely a course you'll take probably as a junior. So I want to make sure you've seen that, and that'll take us into Turing machines and some theory of computation. And I want to talk a little more about recursive functions. I want to talk about Fibonacci numbers and things like that. So we'll work on that over the next 2.5 weeks, and then come back to crypto if time permits. So let's talk about counting. And this is one of these subjects that, we all know how to count. We learned how to count a long time ago. It doesn't sound like it's that complex. But there's aspects of this that will be surprisingly subtle and powerful to work with. So we're going to start with something called the Pigeonhole Principle. So you know what pigeons are, right? They're these little gray birds that fly around. They hang out in parking lots. They're actually pretty cute, and they make some cool sounds, but a lot of people don't like them. And pigeons used to be used for, among other things, sending messages, right? You could train them to go from one place to another. So if you want to send a message some distance away, you could take the message, write it really small, attach it to the leg of a pigeon, and send it to your partner on the other side of town or the next town over, and it would carry it, and they could take it off from there. So pigeons were used for conveying messages. They've been used in times of war to deliver munitions. They're trainable in all kinds of ways. So if you're dealing with pigeons, you need a place for them to stay, and so you usually have a pigeon box with a series of compartments, and the pigeons hang out in there. So here's pigeon 1 and 2 and 3 and so on. And each pigeon gets its own spot in this box. And so if I were to number my pigeons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they could go in different holes, right? I could have pigeon 1 being down here and pigeon 7 being up here and so on. But no matter how these pigeons arrange themselves, if they don't want to share, what's the most number of pigeons I can fit in this box? It's not a trick question. 10, right? So there's 10 spots for pigeons. If I have 10 pigeons, they can each have their own spot. If I have 11 pigeons, they're going to have to share. Okay? This is all the Pigeonhole Principle states. So this says the following: given n containers and n plus 1 objects placed in those containers, the following is true: at least one container has at least 2 objects in it. So n containers, n plus 1 objects placed in those containers, at least one container has 2 or more objects in it. It's possible that one container has n plus 1 objects, right? I might have put all my objects in one container. All this is saying is that at least one of those containers has 2 objects in it or more. In other words, I can't just put one in each container and be done, because I don't have enough containers. But this is the formal statement of that, and once we know the pigeonhole principle, we can use this fact to solve various problems and show various things. And we don't have to prove that this is true, we can say by the pigeonhole principle. Okay, so it's another one of these big hammers we can wave at problems. So how does this work for us? Given 27 people whose names are made up from our standard alphabet, A through Z, at least 2 of them have the same first initial. So when I'm grading papers and I have 30 people in the class and I'm alphabetizing, at least 2 people are going to have the same first initial. And how do we get that from the pigeonhole principle? Well, the way to describe it is make yourself 26 containers labeled A, B, C through Z, and place each person in a container based on what their first initial is. So now I have 26 containers. I have 27 objects being placed in those containers. By the pigeonhole principle, at least one container will contain at least 2 objects. This means one of these containers has 2 people in it with the same first initial. So using the pigeonhole principle is taking your original problem, rephrasing it in a way that lets you translate it into placing objects in containers, and setting it up in such a way that typically one of these containers contains at least 2 objects, and then looking at that and using it to say, okay, therefore the conclusion is true. And sometimes it's a fairly direct map like this, sometimes it's going to be more subtle. But let's do a few other examples. So in any group of 8 people, at least 2 were born on the same day of the week. And how do we get that? Well, make 7 containers, one for Monday, Tuesday, Wednesday through Sunday. Put each person in a container based on when they were born. And pigeonhole principle says 8 people in 7 containers, at least one container has 2 or more people. And since those 2 people are in the same container, they must have been born on the same day of the week. And it could be all 8 were born on the same day and they all went in one container. That still proves our conclusion, right? At least 2 people were born on the same day. All right, and sometimes we flip the questions around. So we could ask a question like this. How many people should you invite to a party to guarantee at least 2 have the same zodiac? There's 12 zodiac symbols. Everybody has one based on when they were born. or think of birth months. So how many people should you invite to a party to guarantee that at least 2 of them have the same zodiac symbol or were born in the same month? And you got to invite 13, and that's another application of the Pigeonhole Principle. Because if you invited 12, it's possible that, each one comes from a different month. But Pigeonhole Principle says if you have 13 people and 12 signs, right? So these are your buckets, these are your objects going into the buckets. At least one bucket's going to have 2 objects, which means 2 people will have the same sign. So if you invite 13, you're guaranteed at least 2 people share the same zodiac sign. So that's your answer. All right, making sense? So there's also a generalized pigeonhole principle. And it follows pretty easily from this. To describe this, I need to introduce a new mathematical operation. This operation is called the ceiling operation. So it's 2 little upside down L's on either side of a number or a variable. So this is ceiling x. And this is the smallest integer, which is bigger than or equal to x. So the smallest integer bigger than or equal to x. So the ceiling of 2.5, what's the smallest integer bigger than or equal to 2.5? That's 3. That's also ceiling 2.9. That's also ceiling 2.99999. And it's also ceiling 3, because the smallest integer bigger than or equal to 3 is 3. But if I go just a little bit beyond that, smallest integer bigger than or equal to this number is actually 4. So it's kind of like the opposite of rounding in some way, right? It gives us back an integer until you get just a little bit beyond the integer, and it'll jump you up to the next integer. Okay, so it's ceiling. The other operation you find is floor, and that's the one that brings you down.
Right side L's?
I don't know. Yeah, I think so. I think it's like, yeah. So floor, I think, is the largest integer less than or equal to your number. In ceiling and floor, they're operations you find in programming languages. All right, so keep the idea of ceiling in mind. Here's the generalized pigeonhole principle. So given n, what have I been working with? N objects, n containers. Okay, so let's say given k objects and n containers, and I'm doing this without notes, so let me see if I can recreate this. Don't write this down until we figure out if this is correct. I think it's going to be ceiling k over n objects. So for example, 5 containers and 11 objects. Generalized pigeonhole principle says at least one container has ceiling 11 over 5 objects. Well, 11 over 5 is 2.1, and the ceiling of 2.1 is 3. So 5 containers, 11 objects, at least one container has at least 3 objects in it. And it makes sense, right? So there's my 5 containers. I want to put 11 objects in. Well, I'm going to start off, I'm going to put 1 in each of these. And now I got to start doubling up, so I'll put another in each of these. And I've placed 10 objects. I've got 1 more object to place. Wherever I put it, that container is going to have 3 objects in it. And it could be more, but it's at least ceiling at k over n. And if you're given this generalized pigeonhole principle, what can you do? If you place n plus 1 objects into n containers, at least one container has ceiling n plus 1 over n objects. Well, what's ceiling of n plus 1 over n? Not necessarily.
Depends on integer.
So n plus 1 over n is n over n plus 1 over n, which is 1 plus 1 over n. And 1 over n is going to be bigger than 0, but it's going to be less than 1. So this is going to be bigger than 1 and less than 2. So this is the ceiling of 1 point something, which is going to be 2. So the generalized pigeonhole principle says if you had n plus 1 objects in n containers, at least one container would have at least 2 objects in it, which is just the simple pigeonhole principle. So that's why this is generalized. It works in more cases, but you can get the simpler version from this. All right, is that making sense? So how many students do you need in a class to guarantee at least guarantee at least 5 have the same first initial? So how many students to guarantee that at least 5 of them have the same first initial? And so generalized pigeonhole principle, k objects n containers, at least one container has ceiling k over n. So our containers are, booths based on your initial, so A through Z, so we have 26 containers. And if you have k students, then the generalized pigeonhole principle says at least one container has at least ceiling k over 26 students. And we want this to be at least 5. So this is basically find the smallest k such that ceiling of k over 26 is equal to 5. And if you play with ceiling, that'll happen as soon as k over 26 is bigger than 4. So find the smallest k such that k over 26 is bigger than 4. Well, if it's equal to 26 times 4, which is 104, That's exactly equal to 4, so the ceiling is 4. But if we go up one more student, 105 over 26, the ceiling will be 5. So 105 students should do it. And you can kind of get there sort of intuitively. Just take 26 people and assume you're unlucky. I mean, your first 5 students could all have the same initial and you're done. But assume you're unlucky. Well, your first 26 students should all have different initials. And then your next 26 should, all have different initials from each other. And so now you got 52 students and each, you only have 2 of each initial. And do another 52, you can have 3. Do another 52, and now each student has the same initial as 3 other people. And you've got 104 people in the classroom. And now if you try to add one more person, they're going to have the same initial as somebody else. And everybody shares their initial with 3 other people. So that 105th person will be the initial where you have 5 students with that. But again, Pigeonhole Principle lets us not have to worry about the intuition or the whys of this. We can just sort of use this as a given. All right, at this point I've got to go get my notes because I want to show you some less obvious examples of this, and I don't have these memorized. So relax for 2 minutes. Let me go grab my notebook.
Did they freaking block out the firewall? I think the only way we can do it is if you guys also get on the VPN.
We'd have to be on the same IP.
Yeah.
Comanche, the old-fashioned way.
No. Do you think they'd let?
Comanche bypasses.
Oh,
Yeah, me neither. That's why I'm done for the day. Me?
They said I carry around a brick everywhere.
I don't have to charge every 10 minutes.
That's karma.
Good job, Aiden.
At least I didn't trip, right?
I mean, kind of.
I didn't fall.
We're all waiting for
Oh!
Yeah, go ahead and fall.
No, you should have fallen because you could have sued.
I could have sued the school.
Tuition free.
Yeah, exactly.
Why'd they put that chair there?
That's not okay.
No.
Damn it, no. No. It's
No, look. Actually, just I might die. Have a pickaxe.
Do you want to fall again?
I didn't fall.
You almost did.
I kicked the chair really hard and it made it sound like I did something wrong. Didn't you hear it? It's like, fuck the chair.
Yeah, nice try.
You know, he's one of the probably still.
Probably.
Dude, he's gonna get demonetized.
Hi, YouTube.
Yeah, you do.
What is up, YouTube? Doing a review on the class. Just to make me the YouTube channel. There we go. Dude, please don't use a pickaxe to mine dirt.
I'll do what I want.
Worse, I'm mining sand.
I don't like sand.
Yes. It's real coarse.
No, just balls.
He needed a joke. Hey, like finally, Anakin, he doesn't like sands.
Yeah, that's the point. That was the joke, that I didn't say anything about
All right, so you want to see some crazier applications of this?
Dude, it's like a squeeze here. Nothing. You wouldn't understand.
Yeah, no, I don't know if I.
Squeeze down, yeah.
So prove that every positive integer has a multiple consisting of only ones and zeros. And this is a little bit of an odd fact. So 1, well, we can just multiply it by 1, and that's a number that can be written as just ones and zeros. What about 2? That's going to be 2. That's not just ones and zeros. Nope. Written as ones and zeros and decimal. 2 times 50 equals 100. That's writable with just ones and zeros. What about 3? Yeah, I know, it's hard. Yeah. I don't want to have to work though. So 111 is 37 times 3. So 3 times 37 equals 111. 4 we can do 25. 5 we can do 2. Thank you. 5 we can do 2. What about 6? I'm thinking I can do 370 divided by 2. So 6 times 185, and that's ones and zeros. So we can do this in some cases. I know how to do 7 too. 7's a good number. So if you do 7 times 11 times 13, you get 1001. So we can do this in some cases, but there's not an obvious pattern here. Certainly not enough that the idea of proving this jumps out, but we can prove this pretty easily using the Pigeonhole Principle. All right, so you ready to see this? So proof. So every positive integer, let's call our integer n, and let's find a multiple of n that's readable as just a number containing ones and zeros. So consider the n plus 1 numbers 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Up to and including n plus 1 ones written side by side. Okay, and those are decimal numbers, even though they just have ones in them. Okay, so place each of these n plus 1 numbers into a container based on its congruence modulo n. So modulo n, everything is congruent to either 0, 1, 2, 3, all the way up to n minus 1. There's n possible things you're congruent to mod n. Mod 3, you're congruent to 0, 1, or 2. Mod 5, you're congruent to 0, 1, 2, 3, or 4. Okay, so we have n containers, and we are placing n plus 1 numbers into those n containers. Pigeonhole principle kicks in and tells us at least one container has at least 2 numbers in it. So PHP tells us at least one container has at least 2 numbers in it. If 2 numbers are in the same container, it means that they are both congruent to the same thing modulo n. Right? We place them into their containers based on what they're congruent to mod n. So these 2 numbers, let's call them a and b. And let's just suppose that b is less than a. So I can call them whatever I want. So there are at least 2 numbers, a and b, in the same container, which means a and b have the same remainder when you divide it by n. Well, if a and b have the same remainder, if they're congruent to each other, then their difference is congruent to 0, or put differently, n divides their difference. That was the homework question we talked about. All right, so what have we done? We've generated n plus 1 numbers containing just strings of 1s, and we've just shown that there are 2 of these numbers, at least a and b, whose difference is a multiple of n. Well, if a is bigger than b, a looks like that, b is going to look like, a bunch of zeros with some 1s. If I do a minus b, what am I going to get? I'm going to get a bunch of 1s followed by a bunch of zeros. For example, if my 2 numbers were this and this, right, their difference is going to look like this. It's going to be a number consisting of just 1s and zeros. And the way we chose a and b, that difference is a multiple of n. So that difference will be a number containing only 1s and zeros. That is some multiple of n. So that proves that there always is a number which is a multiple of n consisting of just 1s and zeros. It doesn't really give us a formula for finding that, but it kind of gives us an algorithm. So let's say we wanted to do this for the number 9. So let's suppose n is equal to 9. So I'm going to take the following numbers, 1, 1, 1, 1, 1, 1. 10 numbers. I'm going to calculate each of these modulo 9. Since I have 10 numbers, at least 2 of these are going to be congruent to the same thing. So this is congruent to 1, this is congruent to 2, and this is congruent to 3. Maybe we'll get lucky here. Yeah, I think there's a pattern here. Let me try this one. Okay, so this is also congruent to 1. So this is congruent to 1, this is congruent to 1. If I subtract them, that should be congruent to 0. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 times 9 is a bunch of 1s followed by 0. So that's kind of weird, right? But in a cool sort of way. What I did where? Here?
Yeah, so I was working with the congruences and finding those, and then
So I cheated. I happened to see a pattern. Right, and this is like the worst possible scenario because I had to do all 10 of these before I found 2 things that were congruent.
okay.
Right, but let's do a case like 5, right? So right, so write down those 6 numbers and look at them modulo 5. Well, this is congruent to 1. This is also congruent to 1. I can stop right there. I know the difference of these will be congruent to 0. So 1, 1 minus 1, that's just 10. That's guaranteed to be a multiple of 5. But I happened to pick a case here where we had to do all 10. So that's a kind of weird application of Pigeonhole Principle, right? You wouldn't think it would come out of counting or a counting argument, but it does. Let me show you one other interesting one. So given n plus 1 positive integers less than or equal to 2n, at least one is a multiple of another. So pick some number n, pick n plus 1 positive integers less than twice n. You're guaranteed at least one of those numbers you picked is a multiple of another one you picked. So for example, let's say n equals 4. Pick 5 positive ints less than or equal to 8. You're guaranteed at least one is a multiple of another. Well, I don't want to pick the number 1 because everything is a multiple of 1. I could pick the number 2 and then I can't pick any other even numbers, but I could pick 3 and I could pick 5 and I could pick 7. And I'm in great shape, but I got to pick one more number. I'm trying to pick 5, and any number I pick is going to be a multiple of one of these, right? Because all that's left is even numbers or the number 1. So maybe I don't want to start with 2. I could start with 3, and then I could do 4, and I could do 5. I can't do 6. I can do 7, and I've still only got 4 numbers. I got to pick a 5th number still, and I can't do it. So this is true for any n. So if you try to pick 101 numbers less than or equal to 200, you're guaranteed at least one is going to be a multiple of the other. And if you play with this, it's believable, right? It seems like this is a lot of numbers to pick. You know, we're tying into prime numbers somehow, because if we pick prime numbers, we know that they're not multiples of anything else. But we can't find 101 primes. But, you know, they don't have to be prime. I could pick 3 and 4. I just have to pick numbers that are all pairwise relatively prime. And I'm claiming you cannot find n plus 1 pairwise relatively prime numbers less than 2n. And again, Pigeonhole Principle will give us a pretty easy proof of this. So let's suppose we've picked n plus 1 numbers, so call your numbers a1, a2, a3, all the way up to an plus 1. So I'm just naming my numbers. Factor out powers of 2 from each. So let's write A1 as equal to 2 to the something times Q1. A2 equals 2 to the something else times Q2. A3 equals 2 to the something else times Q3. And so on up to AN plus 1 equals 2 to the something times Qn plus 1. And these Q sub I have to be odd, because if they were even, we could factor out another power of 2. All right, and I'm not really interested in the powers of 2. I'm interested in these odd numbers. So the set of all Qi is a set of n plus 1 odd numbers, each less than or equal to 2n. And this is where we're going to throw the pigeonhole principle. So how many odd numbers are there less than 2 to the n? So suppose n equals 5. You got 1, 3, 5, 7, and 9. It's like 5 odd numbers less than or equal to 2 to the n. If n equals 3, you've got 1, 3, and 5. 3 numbers less than or equal to 2 times n. So you can convince yourself there are n odd ints, positive odd ints less than or equal to 2n. Well, now we're simply going to take each of our Q sub I and place them in a bin corresponding to their value. And we have n bins to place things in because there's n odd numbers less than 2 to the n. And we have n plus 1 things we're putting in those bins. So Pigeonhole Principle says one of those bins will contain at least 2 objects, which means at least 2 of these Qi are the same. So our original numbers, one of them is a power of 2 times some q. The other one is a different power of 2 times some q. So now this gets slightly technical, but suppose our numbers a equals 2 to the something, let's call it 2 to the x times q, and b equals 2 to the y times q. Well, if x happens to be bigger than y, then a is divisible by b. Right? Because we can, if we take a divided by b, the q's will cancel, and if x is bigger than y, this will be just 2 to the x minus y, which is an integer. And if b happens to be bigger, then b divided by a would be 2 to the y minus x. In other words, if I write this out, it's a bunch of 2's multiplied by q. If I write this out, it's a smaller number of 2's multiplied by q. This is just equal to that times the smaller one. So these original numbers, which were a power of 2 times that q, the larger one is a multiple of the smaller one. All right, so that's the pigeonhole principle. The main deal in trying to use it is trying to take your problem and phrase it in terms of, objects and containers, and then using the pigeonhole principle to say some property about how many objects you have in a container. Or to go in the other direction, you want to prove that you always have a certain number of objects in at least one container, and you run that backwards and figure out what your numbers have to be using the pigeonhole principle. So I posted your next homework set on Canvas already, and I think there's some pigeonhole questions in there. So look at those, and we can talk about them Friday after the quiz. Quiz Friday will probably start about a quarter after, so I can give people a chance to get here late. So we'll spend the first 15 minutes either answering questions or talking about something, and then we'll do the quiz for like half hour, and then we'll continue with lecture after that. All right, good so far? All right, so let's continue with counting. I want to talk about something called the product rule. Not the calculus product rule.
Thank God.
Yeah.
I got scared for this.
Okay, the multiply thingy rule. So here's the idea of the product rule. Given some procedure, P, which can be performed by a succession of tasks, T1 and T2. So some procedure, washing your car, going to vote, making dinner, whatever, some procedure which can be performed by a succession of tasks, T1 and T2. The number of ways to do procedure P is equal to the number of ways to do task T1 times the number of ways to do task T2. So that's the product rule. If you can do some procedure as a succession of tasks, in other words, doing T1 followed by T2, the number of ways to do your procedure is the product of the number of ways to do task 1 and the number of ways to do task 2. All right, so example, 2 people and 20 desks. And procedure P is have these people sit down. So 2 people are going to go into a room with 20 desks, and they're each going to find a seat. And they're not allowed to share a seat. They each have to find a different seat. And we want to know how many ways can this happen? How many possible seating arrangements can we end up with? So we can break this procedure of having 2 people find seats and sit down into a succession of 2 tasks. Task T1 is the first person finds a seat. All right, so I can send these people into the room one at a time. First person goes in, finds a seat, and sits down, and then task T2, the second person goes in and finds a seat. And any possible way that these 2 people can sit down in the room can be achieved by doing that succession of 2 tasks. Right? They don't have to go in at the same time. I can send them in one after the other. Okay, if my only task in life is to send somebody into an empty room with 20 desks and have them take a seat, how many possible ways can they accomplish that task? 20 ways, right? There's 20 desks. They just have to choose which desk to sit at. So T1 can be done 20 ways. Okay, after that person has gone in and sat down, they're sitting at one of the desks. Now I'm sending another person in and asking them to find a place to sit. How many ways can that task be accomplished?
19.
Right, it's 19 because there's only 19 seats available left. So task 2 can be done 19 ways. And so P can be done 20 times 19 equals 380 ways. So there's 380 ways 2 people can sit in a room with 20 desks. And this is useful in everyday life. Okay, and you probably do this already. So you have 5 people lined up for a picture. And they're side by side. Nobody's allowed to go in front or in back. It's got to be 5 people standing side by side. And everybody's pushing each other because they want to be in the middle, or they want to be on the end, or they want to be next to their friend or their enemy or whatever. So how many ways can 5 people line up for a picture? Well, we can break it into a succession of tasks. So task T1, first person, however you decide who the first person is, picks a spot. So here's 5 spots. First person's going to go in and they get to pick a spot and they're going to stay there and nobody can move them. Task T2, second person picks a spot, and so on. And at the end of task 5, everybody has taken a spot in line, and now we can take the picture. Okay, how many ways can the first person choose a spot? Right, so this is 5 ways. How many ways can the second person then choose a spot after the first one's already taken a position? Right, that's 4. Third person has 3 choices, fourth has 2, and whoever was fifth, they don't get a choice. There's only 1 spot left. They can only take a spot one possible way. So the total number of ways you can line people up is 5 times 4 times 3 times 2 times 1, which is 120, which is also 5 factorial. Okay, so 5 factorial means the product of the first 5 integers. That's just a definition. So 120 different ways you can line 5 people up. Making sense? All right, you go for lunch and you're allowed to pick a soup and a salad. And there are 3 soups and there are 5 salads that you can choose from. And you're required to have both a soup and a salad. It's a law. So how many lunches can you possibly get? Well, we can take the procedure of choosing a lunch and break it into 2 subtasks. First choose a soup and then choose a salad. How many ways can you choose a soup? 3. Well, you only have 3 soups. You only get to pick one. See, 3 ways to choose a soup. How many ways can you choose a salad? 5. So there's a total of 15 lunches possible. All right, so it's a pretty straightforward principle. It's pretty easy to apply, and it's kind of obvious in some cases if you just sort of think about it differently. But it comes up in some interesting ways. So how many ways can you create a 4-bit string? So 4 bits mean your string consists just of 1s and 0s, and we want to create something with exactly 4 1s and 0s. So that's our procedure, creating a 4-bit string. We're going to break it into 4 subtasks. Task T1, pick the first digit. Task T2, pick the second digit. Task T3, pick the third digit. And task T4, pick the 4th digit. And once I've picked all 4 digits, I've got my 4-bit string, right? Okay, how many ways can I pick the first digit? 2, it's a 1 or a 0. How many ways can I pick the second? And the third and the 4th. So the total number of ways I can complete this procedure is 2 times 2 times 2 times 2, which is 2 to the 4th, which is 16. This is why there's 16 4-bit strings. Okay, we know that in 250, we know that in computer science. This is another way of seeing that. So let's flash back to 250. So let's take a Boolean function of 4 variables. So there's variable 3, variable 2, variable 1, variable 0, and I want to write its truth table. Okay, how many rows are there going to be in this truth table? Right, it's the number of ways that I can write values of 1s and 0s for these 4 inputs. This is going to be 16, which in this case was 2 to the 4. or for n variables, 2 to the n. And here's my function. How many possible functions are there of 4 variables? Well, that's analogous to the question of how many different truth tables are there for a function of 4 variables? Or how many different ways can I fill in this output column? Well, I know every output is a 1 or a 0. Forget about don't cares. So I can break this into a series of subtasks. Choose the output variable for the first row, for the second row, for the third row, and for the last row. So this task I can do 2 ways, this task I can do 2 ways. Each of these rows I can fill in 2 possible ways. And so the total number of ways I can fill in this output column is just 2 multiplied by itself, in this case 16 times. So there's 2 to the 16th possible truth tables for functions of 4 variables. And in general, if you have n variables, there's 2 raised to the 2 to the n possible functions. So if you had a parts box in 250 that had every possible chip you could have for a gate with 4 inputs, you'd have 65,000 of those chips in your parts box. And they'd have really tiny writing on top. All right, so that's the product rule. Friday we'll talk about the sum rule. Sum rule is when you can break a task into a choice of doing either one subtask or a different subtask. So if you're allowed to order a soup or a salad but not both, that's where the sum rule is going to come in. And it's going to look a lot like the product rule. We'll put those together into combinations, and then we'll move into permutations and other good probability things. All right, I will see you next time.